What's up everyone? Welcome to another tutorial, and today I wanted to go into graphing and data visualization because this is something that I really love to do. So I was reading a paper by Jonathan Lynch's lab at Penn State. One of their papers from 2014 by Alexander Bush and Jimmy Burridge and Larry York and the gang there. They produced this particular graph here, looking at different root traits along the x-axis, normalized mean values on the y-axis. So they were able to produce one particular figure with a bunch of different variables. And so that's something that I wanted to do and do my own little take on it. So I'm going to walk through how exactly I did that. For this tutorial today, I'm going to use this data here. What we have is about 300 different genotypes of soybean. So I'm looking at root system architectural traits in soybean. So these are the different entry numbers of those 300. So from 1 to 300, we have the name of those different genotypes. Most of them are PI lines, as you can see here. And then we have the genotypic based cluster. So I did a hierarchical clustering based on the SNPs for each genotype, and it spread it into 8 different clusters. And you can see here these first genotypes are all actually American genotypes, and they're all put into the same cluster just because of the bottleneck that we have with our American germplasm and soybean. But no matter what type of data you're using, you can do it. So this is the factor that we're wanting to use to cluster it, and then we have the different root system architecture traits that we're wanting to show on the graph. So now the problem we have when we're graphing these, or if we're wanting to all graph them on the same plot, we've got 0.242 grams as shoot weight. The root weight is lower than that, and then we've got length, so centimeters, 200 centimeters, 37 centimeters. So how do we normalize them all to put them on the same graph so that we can compare all these different genotypes and all these different clusters, one and the same? And we'll be using 3 different packages in R today. The reshape package, the ggplot package, as well as the dplyr package. So I'm going to bring in that data set into my environment, name it all data, and get a look, make sure those column names line up with the column names that we're just looking at in Excel, and they do. I want to ensure that the cluster is a factor. So you saw that there was 8 clusters from 1 to 8. We don't want the program thinking that 8 is better than 1 and that they're a numerical order. No, they're just ambiguous numbers that we use. So making them factors is very important. And we can do a summary here just to ensure that those clusters are factors, and sure enough they are. I'm familiar with this data. I can see that there's 8 different factors, or 8 different clusters, and this is the number of genotypes in each particular cluster. So we know that's right, and I can move on. Now I want to scale this. So the best way to do this is using the scale function. Essentially it scales every column of data around 0. And I'm looking at just using the phenotypic data, or the phenotypic traits themselves. So column 4 to column 52. So we can see here we want to ignore these first 3 columns because we don't want to scale those, but we want to scale the root traits themselves, which are these ones here. So we'll run that, and we can take a look at what we produced, and sure enough, here we go. Everything is kind of scaled around 0, and you can see that just from the data output. All right, next we want to take all that phenotypic data and reattach that clustering column, because that's the one that we want to use to graph today. So that's what we're going to do here, is use the column bind function. We've got cluster on the left hand side, then on the right hand side we want to bind it to your phenotypic data, that scale that we just created. And what it looks like now is there, sure enough, we have cluster on the left and all the data that we want on the right. We have a lot of data. We don't want to graph every trait. We only want, say, 10 or 12. We don't want all 52 or whatever there may be. What I do next is, using the dplyr function, or select within the dplyr package, I can then select cluster, and you can see I wanted total root length, primary root length, and I did want root weight. I put it over here. So these are the actual traits that I'm wanting on the bottom, the x-axis. So I'll run that, and so yeah, we have scale data frame piped into the select of the dplyr, and that just renames it scale data frame. And we can take a look at what that looks like. Very similar, it's just in a different order. the order that we want it, and away we go. Next, we have the points, but we want the lines, and the lines between the points are actually the mean. So we want the mean of each cluster, genotypic cluster, to be the line between each phenotypic data point from trait to trait. So in order to make both both a graph with points and with lines, we have to create two different data frames. So I'm going to make the secondary data frame, and what the secondary data frame is going to be a mean based on each individual cluster. So cluster 1 will have a mean for each trait, cluster 2 will have a mean for each trait, all the way down to cluster 8. So that's what I'll do next. Using the scale data frame, I want to first group by the cluster. So use the group by function within dplyr, and then I want to pipe it and summarize each trait based and get the mean for each trait. So the mean for total root length, the mean for primary root length, the mean for root weight, all in that order. And then I can create this new data frame called cluster means. So there you have it. dplyr creates a tibble, and we have 8 clusters. We have the means for each one of those 8 clusters for each individual phenotypic trait. So now we have the data that we can use for the graph, for the lines, as well as we have just basically the raw data of all the different 300 genotypes that we use as the points on the graph. And now we want to put them together and graph them using ggplot. But before we do that, if you've used ggplot before, you know that it's particular in how it wants the data shaped in order to input the data into its function. So to do that, we use the melt function, which is within the reshape2 package in R. And it's a generic melt function. So we have this very wide table, and we want a narrow and long table essentially, and that will make it much easier to graph. So I'm going to take the scale data frame that we have, so for all the different points, for all 300 different genotypes, and we want to use the cluster column as our identity column, and we can build on that. After that function is run, we have clusters from 1 to 8, and then we've got variables and we've got values. So we have instead of having a wide data frame, we have very narrow but long data frame down. So do the same thing here and should get the same output. Yes, we do. So we've got clusters 1 to 8. We've got the average or the means for total root length for cluster 1 here. We've got the mean for primary root length for cluster 1 here, and we've got all the data that we need to graph. So then we pull it into the ggplot function. So like I said earlier, we have 2 different ggplots functions within one ggplot. So we want the geom point to get the different points of the graph, and then we want the geom line to get the different lines of the graph. So geom point would get these different points, geom line would get the average, the mean of the different points across. So first what we do is for data, we want to bring in melted df. So that's our first data frame that we made. And then for the aesthetic, we want the x to be the variable. So we knew the different variables are the different traits. So we want those to be along the x values, similar to in the paper that we were looking at. And you know what, before we go any further, how about I just run this and we can look and see how it worked. So I ran it and came across over here. Okay, so we have lines. Those are the means, and we've got the dots. Those are the actual data points. These are the genotypic data points. So there should be 300 dots essentially on each one of those. So to create the dots, we went through this. We wanted x being the variable, y being the value. We want there to be different colors. As you can see, the different dots are different colors, and they're based on the cluster. So there's 8 different clusters, and you can see here on the right hand side in the legend the 8 different colors. And you can choose what colors you want, and I just wrote them in here using blue, green, red, orange, what have you. And then the points, you can change the different color or different size of the points. You can change the jitter, so you can see that my points on the screen here actually take up a wider area. They're not all lined up one on top of each other. And then you can put the labels in, so normalized blup value on the y-axis, and then the x-axis RSA trait. And you can set a scale here, so I have -4 to 4. And then the line itself, so I use the cluster melt data frame, and then for aesthetics, the same variable and value. I grouped it by cluster, so those are the different grouping variables here in the legend. I colored by cluster as well, and then you can change the size of that line as well. I have it set at 1.5, but that's changeable. The theme is black white, so that's just the background and the color, and if you've used ggplot before, you know how to change the theme. Instead of using the scale fill manual, you have to use scale color manual, and this is just different for geom line and geom point, and it can be very frustrating to know which one to use and when to use it, and I just kind of test until I get it and use the same colors for the lines as I did for the dots, obviously for consistency. The label I have here, genotypic cluster, so using this top is just to make it so genotypic is the top, cluster is the bottom, so it just takes up less area one on top of another. And then here back with your theme, you can change your theme and change the angle or the height or the adjustments. There's lots of different changes that you can make with ggplot, and this is what it looks at the end. If you're interested in removing color from any one of these, and I didn't want the dots to be colored, I just wanted them to be black dots. All I had to do is remove the color equals cluster here, and we got this type of output, which is very similar, just no colored dots. Now, I wanted to go back a few and show you a different graph that I was working on. So very similar data. The only difference here is the data was the same except for the cluster column. So instead of using genotypic based clusters, I used phenotypic based clusters. So the hierarchical clustering mechanism algorithm actually cut the different genotypes based on their phenotype. These phenotypes by and large were segregated based on their phenotypic output. I'm going to cut it off there. If you have any questions or comments, leave them in the discussion below. If you'd like to know a little bit more of how I clustered my data using hierarchical clustering or wards declustering, feel free to look at my other tutorials. You can see them also in the description below. Other than that, have a great day.